Are you looking today at triangles and special constructions for triangles where we try to locate the center of a triangle? And the thing about centers of triangles is there are lots of them. It's not something like the center of a circle, which is very clear cut. There is only one center to a circle. How do you define the center of a triangle? Well, it turns out there are lots of different kinds of centers. Some of the centers have been known for thousands of years. The ancient Greeks knew about these centers. So for this triangle, I just drew very carefully a scalene triangle, kind of at random. And what I'm going to do is construct the perpendicular bisectors of each of the three sides. So that means I'm going to treat these as line segments, and I'm going to do my perpendicular bisector construction. Should be familiar. So I put my compass point at each end of the first side here and construct these two crossings above and below it. I can do that for all three sides. It's going to get a little bit busy on the page as I do this, so we have to be careful to keep it all straight. That one's not great. Losing track of where I'm going. Alright. So then I have to go back and say, well, I want to get the perpendicular bisector for this side. These were the two construction points that I located for finding that. So I'm going to line up my straight edge on those two intersections. And there's the perpendicular bisector. Oops. Okay. So that should be perpendicular and it should bisect that side. Now this side up here, I've got this crossing and this one, which is a little hard to see because it's actually blending in with the side of the triangle. That's all right. Deal with that. So this is perpendicular, divides that into two equal parts. And then the third side. I've got this crossing here, and this one up here. Line it up. All right. So they appear to meet at a point. This is a point where three or more lines, meet together. It's a point of concurrency. Now, let's think about what we've just done. If I look at this perpendicular bisector, let's finish this one off here. It's 3 ticks over there, 3 ticks there, and it's perpendicular. If I look at this perpendicular bisector, every point on this perpendicular bisector is equidistant from the two endpoints of the side. Every point on this perpendicular bisector is equidistant from the two endpoints of its side. And every point on this perpendicular bisector is equidistant from the endpoints of its side. So, this wonderful magical point where all three perpendicular bisectors meet is the one point that's equidistant from all three vertices of the triangle. And that means if I put my compass point here and measure out to one vertex, I should see the same, did I get that right? Yep, I should see the same distance to that vertex and that vertex. And I do, and I can demonstrate that further by actually constructing a full circle using that. So, you make this nice circle, and this circle touches the triangle at all three vertices. It goes around the outside of the circle. So this is called a circumscribed circle. Circum, go around. And this in turn is known as the circumcenter. So if you ever have a situation where you want to find the one point that's the same distance from three other points, what you're really asking for is a circumcenter. It's the point that gives you a circle that would pass through all 3 points. And you can find it by doing this construction. Turn those 3 points into the 3 vertices of a triangle and construct the perpendicular bisectors of each side. And where they meet is the center of that circle that goes through all 3 of your original points. Circumcenter.